All right, so a DC motor. What does DC mean? Direct current, meaning that it doesn't oscillate like we were kind of describing this speaker thing to be doing in order to produce sound of a given changing frequency, right? So it's not oscillating. The current is just going the same direction all the time. You're not switching the direction of the current at any given rate. Same direction all the time. Okay, so this is awesome to me because given some very basic materials, just like with the speaker, you can create this. You can create this. The speaker is a little harder because you have to have an oscillating current. So that's the last thing that you didn't, you may not be able to produce as easily. But for this, a battery actually would do it because a battery produces direct current, right? So there's a positive terminal and a negative terminal to a battery, and so it always has the same direction of current that would flow, right, from the positive to the negative. You'd have to flip the direction of the battery to flip the current, and so as long as it's connected in the same way to the same ends, then your direction of current would be from positive to negative terminal of the battery. So this is DC. Okay, so we're going to make a DC current-based motor, or we're going to describe the schematics of it. So you have your battery, this positive terminal and negative terminal, right? And then you have some kind of contact area thing here, right? So this isn't a circuit element or anything. This isn't a symbolic. This is just a big chunk of metal, right? Or some chunk of metal that, let me do it out here, that can make contact with stuff, right? All right. So if we touch these two pieces of metal together, then you'd get a closed circuit and you'd actually get some current. But we're not done with our schematic, so there it is. So here we are. We have these two contact bits that are ready to go. Now, I'm going to use two different colors just to help describe what's going on. But the red and the blue that I'm going to use for this, well, I'll use two different colors because I'm going to use red and blue for magnets. This color and this color don't mean anything. All right, they're just to describe things. So we have some thing that is going to look like like this, right? Like this, kind of like a little bridge. And then it's going to have a wire that's attached to it like this, and it's going to go on to the rest of it. And so this thing can rotate about this axis is the idea, right? And so it just can make contact all along this little bit. So I'm going to draw that the best I can here, and it makes contact with the white kind of thing like this, right? So it makes contact. Let me draw it maybe a little more convincingly. Makes contact. And as it rotates, it makes contact that whole different way, along that whole semicircle, half circle. All right, and then we have this half of the loop. Then our other color here, same deal, semicircle deal here with a gap between them. And then we have this whole part of the loop. All right, it's all just metal, right? This is metal, it's just a wire. But the two different colors are used so that I can rotate it and show you how and why it rotates. Okay, then we're going to have a north, let's see, where do I want this? How about a north up here? It works both ways. North here and a south here. These are just ends of a magnet, right? Boom. So you can purchase these little, strong rare earth magnets, right, that have north end and a south end on them. They're just really strong. So you know, there'd be maybe south over on this side, but it's facing the other way, and there'd be a north over here, right? But it's facing the other way. So the south is facing towards our circuit on the bottom, the north is facing towards our circuit on the top. Okay, so while this thing is this part is making contact, and here also this part is making contact, we have current flowing along our circuit. So what color do I usually use for blue? Well, blue is used for both south end of the magnet and current. Sorry about that, but hopefully through context. So then the current kind of, you know, travels through this thing, and it travels into this loop. And it goes around, and it comes around, and then it, you know, goes through, and then it continues, and then goes to the negative terminal of the battery. So current flows along that loop, right? So now, what magnetic field do we have? The magnetic field goes from north to south like this. I'll just draw 3 of them. All right. And, oops. And now we see what kind of a torque is experienced. So we can work up our way segment by segment and describe the force with our right-hand rule, but we have a quicker way to it, what we just learned with the torque. So let's figure out our mu vector, and then we can figure out our torque. So with our right hand, we're going to curl our hands in the direction of this loop, which we're just going to consider this portion here, right? But of course it's this whole dealio, but we're just going to consider this portion. Curl your fingers around, so that would be around this way. Your right hand and your thumb gives the direction of mu, which is into the page. Right? Mu is into the page. So now, with mu into the page, what is the torque that is experienced due to that mu? So torque is mu cross B. So now put your fingers in the direction of mu, which is into the page, and then curl them towards the bottom of the page, which is in direction of B, the magnetic field. And your thumb of your right hand points in the direction of the torque. And so the resulting torque, do yellow, torque, is in this direction, right? Mu cross B produces tau in that direction. Okay, and that means torque in that direction, right, means that it is rotating this whole thing, what color do I want to use? Just white, about this axis. Actually, I should have done gray. About this center axis, which this thing's free to rotate about, it's rotating like this, right? So, so let's back out of the torque thing and make sure that we understand, you know, on the level of forces. So let's look at just this segment right here, right? So just that segment right there. We have current to the right, that's I, and the force that we're looking at, trying to figure out the direction of, is IL cross B. So we have our I, and then we have B down towards the bottom of the page, B, and so using our right hand rule, this orthogonally type 1, pointer finger in the direction of I, middle finger in the direction of B, and the resulting force force is into the page. And so this thing is motivated to move like this. We're describing the same thing that the torque already got us. I'm just kind of going back and going granular about it to make sure that we understand. And then down here, looking at this area, that segment, right? So this is this force. Down here, we have current going this way, I, which isn't a vector, L is the vector, IL, and then B traveling in the same, pointing in the same direction, B field. And so what's the resulting force? Point your pointer finger in the direction of current, so to the left of the page, middle finger in the direction of the B field to the bottom of the page, and the resulting force is up out of the page, so a circle with a dot is the force. And so this would be out of the page like this, right? And so now you can see why it begins to rotate in the direction that I described here. And maybe to help, I'll do the gray line over it like that. So it begins to rotate in that direction. And then if you can imagine, when this thing rotates 90 degrees from where it's pictured, then these plates, let me draw a view of if we were looking at it like this, if this was our eyeballs, we're looking at it like this, or from the other side maybe, looking at it like this. I'm going to draw that down here, and just focusing on this part here to see what happens. So we have this plate like this, and we have this thing like this, and if it's rotated 90 degrees from how it's pictured there, you would have these contact blocks connecting both of them. And so the current, right, the current, which, let's see, so this would otherwise continue on to the rest of the circuit, right, and do this. And this is connecting to the battery over here, right? We have some battery. Boom, boom, boom. But it's making contact. So instead of the current going from the terminal, positive terminal of the battery to down here, it doesn't do that. It goes and just cuts right across to here and continues here. So it shorts this whole area. It does not travel into that other area. It just travels around this small loop like this short little segment, because our contact blocks are making contact with both the green and the pink portions of that loop, so it kind of cuts it off. And then it rotates another, so therefore there's no torque on anything because there's no current any longer here that is causing a magnetic force on that loop, but there's some momentum, the thing was spinning, and so it kind of continues to spin, and eventually it spins further enough so that the contact plates aren't making contact with both of them, it's just making contact with some of them. So then at a later time you have, your battery, here I'll just do this, your battery, and you have your contact plates, and then you have, I guess if it's rotating this way, so then that was in the back, I don't know which way we're looking at it exactly, but then at some point you have this situation again, where this then goes to the rest of the circuit, and this here, where this then goes to the rest of the circuit, in which we have a north and we have a south magnet here, right? It causes the torque again. So that is how, and so then it keeps spinning, and it's the same direction that it keeps spinning. So that's how a DC motor works, a really, really simple DC motor works. If you have a battery, and you have some wire, and you have a north and a south magnet, and you can configure, you can configure some contact plates to make contact in this way here, so that it can kind of, and you have some way to have it, spin around some axis. Then you can create a DC motor. So that's to me incredibly cool. Obviously, you can't throw that in a Tesla and go 0 to 60 in 3 seconds, but that gives you a basis for understanding how these electromagnetic interactions can produce some really useful stuff. All right, that's it for today.